All right, everyone, let's continue our conversation on controls. All right. And here I have a signal that I've taken a system and I put a 1 volt step function into it. And this is how the signal is evolving over time. Can anybody tell me whether it's the system is stable or in control, or is it out of control? Oh, it's in the chat. Yep, it's in control. Can anybody tell me why? What is the evidence? I see a lot of oscillations there. Yep. It eventually settles to some kind of DC. All right. So since the system is in control and there's some kind of ringing, can it be a first order system, or can it not be a first order system? Should just keep the chats open. All right, I've got one can't be first order. Yeah. So when you see oscillations, that means there's poles that have imaginary components, right? And imaginary components always come in pairs, right? Because you're taking the square root of something. So you get the positive and you get the negative part of it, right? And so therefore, there always is a minimum of 2. Now you can have a third order system that has a pair of complex poles and then the other pole has to be real, right? But yeah, because you see that oscillation. All right. So, oops, wrong one. All right, what about now? In control or out of control? Yeah, it's in control. Now you just saw me change the circuit, but is it second order or first order? Yeah. Okay, so the thing is right, second order circuits can be over, under, or critically damped. So just because there's no oscillations doesn't mean that it's not a second order. It's a little bit tricky because it looks very close to a first order, and the only way you can tell is right here where you're getting this kind of shape, where a first order it would just come straight up. All right, so all right, so if I made that even bigger, right, it's taking a longer time to get where it's going, so just let me give it a little more time. And now I'll just zoom in here. And I'm telling you, you can't tell. I can't tell whether this is first order or second order, right? Because what can happen is when a system has two real poles and it's very overdamped, one pole is a lot faster than the other. And so it decays so quickly that you don't even notice it. And so it almost looks like a first order system. And of course, the only way to tell really is the Bode plot. Right. So I believe that was 1,000. Oh, not 1,000 K, just 1,000. Okay. And I can tell, right? I have 0. Then in the phase starts to go to minus 90. And then it goes again. And so what it is, you'll see the second kink right here, right? Almost can hardly tell, but in the phase, you can see it goes from 0 to minus 90, and then it holds on a little bit, and then it's going more. Now you don't see it go to minus 180, but it is. So I can tell that that's an overdamp system just for looking at it, right? Now, yeah, okay. Now here, it goes from 0 and kind of smoothly is going to near to 180. The thing is in this regime, it can be really hard to tell, is it critically or over? It's just so in fact, after the midterm, I'll show you how to do it, but you can't just look at it and tell, right? You have to do a few things. All right. But here, oh, which one? Wait, which one? Okay. Yeah, there's this resonant peak developing, right? And so I know that it's definitely overdamped, underdamped, excuse me. And that phase gets tighter and tighter. Now, what if I had 0.1? Okay. So we're starting to see a lot of gain at that frequency. Oh. Excuse me. All right. And it's getting quite sharp. All right. So, but now let's look at that in the time domain. All right. So it's oscillating, sure, but it does eventually, over time, right? It's decaying. And so that constant value that it's headed towards is 1. So even though that's a lot of oscillation, it's still in control. All right, what if something happens to that resistor? Okay, is this system in control or out of control? Okay. So what is your evidence that it's out of control? Okay. So it's true. It doesn't go to a constant. It doesn't settle, right? Yeah, Lionel, that's great. The range showed. Okay, that's a great thing. But what, so that's what it's not doing. What is it doing? What's the word? Oscillate. Yeah. Okay, great. So now I have a few more questions. You know, I might have had something plugged in and you guys might have been talking and I might have not heard a word you were saying. Let me make sure. Microphone, speaker. Okay, so I'm sorry. I wasn't ignoring you. Okay. Running out of colors. So these are the poles. Okay. So these red poles are purely imaginary. These pair of green poles are real and different. This pair of real poles are real and the same. These pair of poles are complex, right? Conjugates of each other, and they're to the left-hand side. Here I've got a pair of poles that are positive and different and real, repeated and real, and complex, but everything here. So which pair of poles are we talking about when we see this behavior? Hey, Gilbert, can you, I don't know if you can see the screen, but can you tell me the red, the yellow, the green, the blue? Which one do you mean? Yep, it's the pair of red poles or the x equals 0 poles. It's purely imaginary, right? things that are imaginary oscillate, right? Things that are imaginary store energy, they don't dissipate it, right? So, yeah. Okay. So that's really kind of the whole thing front and back. Now, so let's just put, the red poles, and then H of S would equal, all right, that would have been the transfer function, right? There's no S term, right? So it just keeps oscillating back and forth, all right? Okay, so let's say I want, to make a non-inverting buffer. Now I know there's one way, right? Let's turn that off, right? Right, but I want to try it another way. I want to see if I can do this. Okay. So the difference is I've got positive feedback. All right. So I've drawn the circuit. This is the Bodhi plot. And that's out. And I got a low pass filter, but should I be surprised? What do you think's going on? Why I want a constant gain, but it's rolling off at high frequencies? What's the thing that's causing that? Or what are the limitations, right? Right. There's many limitations of an op amp. There's power supply, there's input resistance, but which particular limitation in particular? One that in gain bandwidth. Yep, you got it. So it seems like it's working, right? If I click over here, excuse me, 124 nano dB is effectively 0 dB. All right, well, that looks good. Everything, yeah. Hey, I'm a great inventor. All right, so let's do the step response. I just need to change this a little bit. Okay. There's a step. So, okay. So it goes from 0 to 5. Okay. I see something going on here. Let's see, what could I have done wrong? All right, I wanted a gain of 1, right? But I seem to Okay. But no, I mean, this should have given me a gain of 1. All right, did I put in the wrong thing here? No, the step is 1. All right, well, let me see. Maybe I set the power supply wrong. Let me go from plus or minus 10. Huh. Goes to 10. And it just goes up there kind of no matter what I do. Now, all right, let's try minus 1 to 1. Let's just see. Oh, it's still going on. Let's see. All right, let's just sweep the whole thing. But it's just not working. All right, well, I'm looking at the Bodhi plot and I'm noticing that the phase is doing something. I'm starting at minus 180 and I'm going to minus 90. But wait, I thought low passes went from 0 to 180, right? So in fact, this phase 180 can also, minus 180 can be 180, right? And so it's really going from 180 to 90, which really means there's positive feedback, not negative feedback in this case, right? And so something's not right. Okay. So let's try to find out. But so I mean, I have this problem, and let's see what the problem is. All right. So let's try to use our system analysis, and the op amp, right, has a summer. It has H of S, right? And then I have my 2 resistors, beta, but it's going in on the positive side. Okay. And here's my N. All right. And let's use a simple model where it's just open loop gain over S. All right. So anyway, V out equals Vn times H of S. So V out equals Vn H of S. Okay. But it also equals plus V out beta H of S. Let's collect the V out terms. V out 1 minus beta H of S equals V in H of S. And then I'll just finish it off. V out over V in, the whole transfer function equals H of S 1 minus beta H of S. Let's substitute that in. Okay, we substituted in our model for the op amp, right? We get, that's good, S, that's minus beta AV. Uh-oh. Well, the inverse Laplace transform of that, right, is going to be something E proportional E to the plus beta AVT, which is that, right? Now notice the open loop gain can be 800,000. Beta might be 0.5, right? Or 1, but it's just and actually I simplified it just so you know. The N Oops. Okay. I kind of simplified it a bit because there's an alpha, and that's R2, R1 plus R2 here. Okay. So that in fact, there is an alpha here. That's where beta equals R1. But in this case, they're the same, so it's 0.5. Okay. So really, this isn't the important part. That's the important part. This, right? So that would be the alpha there. So this is gives us a pole on the right-hand side, which has exponential decay. So though, even though beta is going to be a half, this could be 800,000. So it's going extremely fast, maybe so fast that the simulator, in fact, is stepping over it. And I have to play a trick and say, the maximum timestamp is 10 picofarads. Let's see if I can see that. It's taking a little bit longer. There we go. And I'm just going to stop it, right? So in fact, you can start to see the exponential growth there, right? Why is it turning into a straight line? Well, op amps can only, output voltages can only change so fast. And so in fact, that's a limitation that you'll learn about in 122. But there's that exponential growth there, right? It's positive feedback. Okay. So now, right, this is the power supply. I'm getting a shape kind of like that. Which ones could it be? And I'll put another one out there. Just a single pole. Where do you think that pole is? Right? If I'm getting something, I mean, that's proportional E to the plus T, right? Which one do you think is going to give that to me? There's a hint. Nobody? Am I going to start calling out names? let's see who's here. Let's see. How about you, Devin? What do you think's going on? Which pole or pair of poles or whatever is causing this exponential increase?
I'm just gonna take a guess and say 2.
This is x squared. It's not necessarily 2.
Oh, I got it.
Can you just shout out a color or something?
I'll say the blue x above x squared.
These pair of complex poles?
I think so.
Yeah, it could be. Even though these would oscillate, it could be increasing. So yeah, you could have a cosine on you. This would be kind of a plus t cosine something. And this is oscillating at a much slower frequency that this is rising, and you couldn't tell. So in fact, it could be anything really. All right. But we did just do the example. So which one, according to the way I worked it out, is it? There's h of s right there.
The orange?
Yep, orange.
Do you mean these guys here?
Oh no,
No, on the right.
on the right side, the axis.
Oh, these are orange?
Yes.
Okay. So it could, if this was a pole by itself or this was a pole by itself, yeah, it could be, right? Now, yeah, the way I drawn them is like they're a pair, right? But I drew a green X out here for like a pole on its own. But yeah, you're right. If you don't necessarily know, those could just be 2 poles, right? But yeah, one of these by themselves, yeah. Yeah. I'm just reading a question here. Do we need the axis for the signal in order to determine whether there is a shift or not? I'm not sure if I follow, because I'm not really thinking about shifts. It's just this isn't what I would call a shift. It's just like I mean, there is a simulator issue. It's not perfect, but I can just tell that there's an exponential increase that then it turns into a straight line. But that's how I know what's going on, right? No matter what, it goes to the output rail. It would go to infinity, right? But it can't. Right.
Wait, so which points
Not
on
realistic.
which points on the graph is it supposed to be?
Well, I mean, this graph or the other one?
On the other one, the one that you
okay.
drew, the one with the cutters.
Okay, all right.
That's a good question.
Now, what I'm saying is, to me, this one's the best because I know that beta AV is a very large number, right? So it's over here. But if I did this,
Ow.
okay, here's another set of axes, and I just did this, right? Which one is it? You have no idea. You know that it's here, but there's no information. And even in the plot where it goes here, then it's exponential, and then it's straight, that's so difficult to interpret, that no, you don't. And here's the thing, you don't even care. The system's out of control. It doesn't work as a buffer. Now, here's the thing. This circuit actually does work. And let me set up the simulation so that you see it. But I'm just going to do 1, 1, 1, T on 0, 2. Stop time. Okay. So it's there it is, it's going off and on, right? But now I've got kind of a linear ramp that at some point, right, it goes high, or some point it goes low. Now, if I just change that axis here, okay, so this is V in. And if V in is going this way, it starts low and goes high, it trips here. If it's high and then V in sweeps low, it trips here. And that is a Schmidt trigger. And it's a way to get rid of noise. I even had do some research with it. And you used to use it in 118. Now you're using the FPGA boards, and I'm not quite sure if you use it there anymore. Although the chip is using it, you just might not be told about it, right? The field programmable FPGAs. All right. So this thing has positive feedback, and it kind of has a memory. It has two states. And if I'm low and go high, I trip this way. If I'm high and go low, I go here. And it's actually a pretty useful circuit. It's useful because it's got the positive feedback, but it's not useful. But the thing, as useful as it is, it's not in control. All right. Now that might have been a bit much, a little bit extra. And they'll go over that even more in EE 122, right? But I do want to come back to here. All right. So here we have our mass spring damper. Vx and velocity are the equivalent. The damper is a resistor. The spring is an inductor. And the mass is a capacitor, RLC. Right? Now, what if this was a tire? And this mass was 1/4 of a car, right? And then these are the shock absorbers and the springs, right? And if this, we're only concerned about the Y direction, but if this goes over a bump, right, Vx is going to get a step, right? Or impulse, actually, because it'll move. It'll instantaneously move, but then the velocity in the X direction will stop, right? But it changes instantaneously here. All right. So anyway, we talked about a step. And we talked about overdamped, critically damped, and this, right? Well, that damper, right? A resistance impedes it, right? So the bigger the resistance, the less current flows. But in the spring constant, it's more like admittance. How easy does it flow, right? So if B equaled 0, nothing flows, right? The resistance goes to infinity, right? So what if this resistor, this damper, what if it failed, right? And now it doesn't pass anything, okay? Right? Well, that would make the resistance infinity. And then this resistor would just be disconnected. Right? And we have this, and nothing's going to happen, right? If this no longer passes Vx onwards, well, then it might as well not be there. Okay. So that's if it fails in a way that it doesn't pass. But what if it fails, right? That it doesn't slow it down at all. It passes everything, right? If it's passing everything, that's like infinity, right? If it's passing everything, well, there might as well be no damper there at all. It's as if it were connected by a steel rod. Well, then that means resistance is 0, right? And we have this, and we have our out of control system. Okay. Let's do a slightly different example. Bx. Damper, spring, mass. All right. All right, that's the equivalent circuit. Right? Well, now let's think what happens. What if, again, if B equaled infinity, right? It passes everything, right? So that means R equals 0, right? So if R equaled 0, that would be a short across the resistor, which also shorts the inductor, right? And it just means that really this mass is connected to the platform with a steel rod. Okay. Now again, what if, let's think about it again. What if B equaled 0? It doesn't pass anything. Right? If it doesn't pass anything, that means it broke. Right? It's just not there. Right? So if resistance isn't there, right, then that resistance, you just take it out. And you're left with this, and it oscillates, right? Now, yeah, And it's kind of the same thing for the K, right? Let's say if the K coefficient goes to 0, that means the inductor is going to infinity. And the inductor's out there, and it goes from a second order circuit to a first order. All right. Yeah, let's think about that. But I'm only going to talk about it. Let's just talk about the damper, right? So that damper passes X to Y, right? Freezing, which means it moves, right? So if it freezes, what's freezing? Well, that's like a steel rod, right? That means B, everything is passed. An infinite amount of is passed, right? That means the resistance is 1 over that, which is 0. It doesn't slow it down, right? Now, what if I had a damper and it didn't pass anything? Well, how would that be? It breaks. It's not there anymore. All right. So B becomes 0 and R becomes infinity, right? And you take R out. Here, replace R with a wire. All right. So in this case, right, you get that, right? In this case, right? So in this case, you could say it breaks open where it's just not touching. Here is it breaks and freezes together, right? Becomes solid, right? It's just a steel rod. And here they're completely disconnected. Okay. Did that answer your question, Karan? When something freezes, does that mean it broke or that it is short? So it's a bit mixing and matches. Something fails, right? And does it fail by breaking and leaving the system? Or does it fail by freezing, right? It passes everything, right? So if it freezes, it turns into a solid rod and resistance is 0. If it breaks off, right, and goes flying down the highway, it's no longer there. And so now the resistance is infinite. So you can kind of take it out of the circuit. Okay. I want to see something else. Okay, so this is a high pass filter, right? It's in control. It changes, but then it settles to an output value. And now there's the high pass version of that, right? Now, what if I start kind of adding things the wrong way, right? This is all supposed to be negative feedback, right? Well, what if I took this and added it to the wrong side? And you say, well, now you've got one input here, 1, 2, 3, 4 inputs here. I need 3 to balance it. Okay, I'll balance it. Sure, why not? Okay, so V in is a step response. It's on for 1 second. I'm only simulating for 1/10 of a second. And I'm kind of seeing this weird behavior. But is this in control or out of control?
That's out of control.
Yeah.
Yeah,
Right.
that's true.
Yeah. Right. And then what if it's just missing? I wonder what happens there. So I can get rid of one of these, right? Still out of control. Right? So put it back where it came from. And we're back in control. All right. So
So what did you put back exactly?
it's eventually settling to 0 if I let it run long enough.
No, he asked what you put back to put it.
Oh, to the original circuit where this is an inverting integrator. So I keep it inverting. Inverting times inverting is non-inverting. I need to make sure it's being subtracted. So I come in on the negative side. But now I have 3. It's inverting. I want to keep it that way. So I come in on the positive side. And then here I have an even number and I come in on the positive side. All right. So you can see that it's pretty important to get that right. I'm just making up some numbers here. So what if I wanted to turn this into a DF2 circuit, right? By now, there's finding out where everything comes, but then you kind of know that, well, it's second order. That means I need to have two integrators, right? I see a 2 here, that means two integrators. And so I would just draw those first. Right? This is all, these A terms are all negative feedback. Well, then that means I have to have a summer, an advanced summer, right? And that this will give me this first one will give me A1, but it's already minus A1 because it's inverting, right? So that's good. This is minus times a minus integrator. And now I have to make sure that it's negative, right? Right. So now I have 1, 2 inputs here, 1 input there. I need a dummy. Okay. So that's how quickly that can be drawn. Right. But now this node here will be the highest order. So that'll be, this is the S squared, this is the S, and this is just a constant, right? Now, I have it memorized. Where does that come from? Well, you divide by the highest order of integrator, right? So I divide S squared, so I just divide everything by 1 over S squared. So I get 1 plus 1k divided by S squared. I get 1 plus 500 divided by S plus 1k divided by S squared, right? And now you, because it's all in order, that's 1, which relates to S squared, right? That's 500 divided by S, right? Because that's an integrator. And then this is 1k divided by S squared, right? But it's in the same order, is that this would be 1. There is no S term. There's something over S squared here. So the thing is I need a summer here to add these up. Okay, let's add them up. So this is non-inverting. I want to keep it on the non-inverting side. All the A's are negative feedback. This isn't feedback, it's just positive. It's feed forward, right? So if you see a plus sign, it's a plus sign. Here, pluses are minuses and minuses are plus, right? And then here too. Okay, I have 2 inputs. Then that means, you know, I need those dummy resistors. And this is out. And so the thing is this is almost an algorithm. And because it's take home, you probably just have that even already written down. But the real thinking is, do I taking here and here? What do I do? All right. And if the output is coming from here, you're going to have to invert it. All right. But okay. So you got to make sure everything's in the right order, right? S squared, S to the 0, right? So this becomes A1, this becomes A2. Here, this is B0. There is no A0. because it's always scaled to be 1. All right. And you don't feed back the first thing, right? So it just doesn't exist. But that's B0. And then this has no S. So that's B2. Why not B3 or 4? Well, because that's the highest thing it can go up to is the order of the filter. And notice there's no S term. And so B1 equals 0. It's just not there. Right? Or another way is if I put B0, and I'll just do it longer this time, a bigger example, B1 S cubed plus B2 S squared plus B4. And sorry, I forgot B3S and A3S, right? So really, this is all set. The kind of filter you have is based on these constants here, right? So if that's not here and that's not here and that's not here, right? Well, I have B1 S cubed and then I have a B4. But what if I see the question, just let me finish my thought. But what if you see something like this? Here's the denominator and I have 1,000 S cubed plus 100,000, right? This is S cubed here, right? I know that it's to the 4th order. So I know that if it's supposed to be 4th order, right, that means B1 will be to the order -1. And so that becomes B1. And then the last thing, right, is the order of the original filter. And that should be 4. All right. So there's no S. So that becomes B4. Sorry, there's a lot of chats. I should get to that. Yep. Okay. Yeah. No, let me just wait 1 second. I'm answering the chats. So when things freeze, it's the resistor's fault. Well, the inductor could break. I mean, the spring could break. The spring could rust and freeze, right? Anything can break, right? Even in a way, the mass can break, right? But now what would that look like? Right? I'm just going to put the mass here. Well, what if it breaks into 2, right? Right? Before it was 1, and then half of it fell off. Oh, well, the mass, so there's a mass still connected, right? Or what if what if I stand on the car and I start jumping, what if I stand on the car? Well, that's certainly a lot of mass that I just put on, right? And just as a quick review, that could be a tire, the mass could be the car, and that could be the suspension. Now I'm standing on it. Well, I've changed the mass, right? It's not broken, but I've changed it. And what if, I don't know. And this is why I'm in engineering, because that's an elephant. What if the elephant sits on it, right? You've really changed the mass, right? And also some nonlinear things would start to happen if things just move so far that then they stop moving, right? But it's a good way to think. And red, you're right, that was supposed to be F4, S to the fourth. Okay, so there was a question, I believe. I cut you off a little bit. I don't know who it was, though. Well, for the mass spring dampers, it will always be a voltage source. Right? Will we always have a voltage source or a current source? Well, if you don't have an input to any electrical system, then, you know, nothing's going to happen. But in the context of the mass spring dampers, it'll always be voltage, not current.
I had a question. For the J omega and sigma and chart or graph with these solutions posted with the different colored solutions, is there like a table with each color going with an equation?
I'm sorry. Where'd it go? This?
Yeah, so I
Well,
see
no,
like,
that's the homework.
oh, okay.
Yes, there will be, because you're going to create it for your study guide. And if you, okay, I'm not trying to be cute, but
Was that homework 9 or homework 10?
this is 10.
Okay.
So you should be able to do 10A and 10B now.
All right.
9 was the Fourier constants. All right. And pretty much today we hit questions 1, 2, we hit 4 out of 5 questions on the midterm. So Monday will be the review and Wednesday will be the exam. So Corinne, your question, not necessarily, you don't always need to be summer. Okay. So now there's some rules of thumb, but if it's a high pass filter, right, and B naught is 1, you can make it that you don't need a gain stage. But if it's a high pass filter and you need some gain, right, you want to multiply it by 10, yeah, you're going to need kind of a summer, but it's only summing one thing and then multiplying it by 10. Now for the low pass filter, right, if you have an odd number of stages, you're going to need something to invert it, right? Otherwise, you don't need one. But again, if you need gain, you're going to need it's essentially a summer that's only summing one signal and provides gain. All right. And what do I mean by that? This, right? It's summing in and it's summing this 0 and it's providing gain, right? And it just, and I'll just leave it at that. Okay. Now, yeah, the band passes, they seem to be on odd stages. So you always need to invert it. So you'll need a stage. But the thing is there's not quite an infinite variety, but you need to be able to determine, is it positive? Is it negative? What do I add? What I don't add, right? Now, yeah, let's say you put a summer that wasn't needed, but the circuit was still correct. I would mark it correct and then tell you don't do that. You're wasting an op amp. Okay. You might get a note, but really it's best not to use op amps that you don't need. What I urge is trying to do problems and understand the process